Hi all. Bad news is that there was no sound with the class recording yesterday. The good news is that I've decided to record a shorter summary of what we did yesterday, or at least the most important points as they relate to your homework. So let's get into it. I'm going to start with a review of the simple one-way ANOVA with random effects. That's what we often call the unconditional multi-level model. And I hope you can see it here on our screen. So here we go. Again, we have a really empty model here, y sub ij, and just to remind ourselves, the I here stands for individual and the j stands for cluster, or in this case, we're talking about schools because we're using that HSB example. So we're saying a person I in cluster J's score on the outcome variable y, that's really what y sub ij indicates, is a function of, is equal to, right, beta sub not j plus r sub ij. Now, beta sub not j is just the intercept, right? And again, we talked about this yesterday. It's the unstandardized regression coefficient for the intercept. And the j here indicates that there's actually a separate intercept for every school, that we can conceptualize having a different intercept for every cluster in our sample. And that's really what makes this different, right? Then the r sub ij is just the residual or the error term. But here we're going to see that we have multiple residual or error terms. So this r sub ij is really the deviation of person ij's score from the predicted score. But here the predicted score is just a function of their school's mean, right? So you can think about this as, how much does person I in cluster J deviate from their cluster's mean, which is really what the beta not sub J is giving us. And then if we look at the level 2 equation, we see that we're going to take beta not sub J, which was a predictor in the level 1 equation, and we're going to make that an outcome variable in the level 2 equation. And now we're predicting beta sub not J, the cluster mean, right, or the cluster's intercept, is a function of gamma not. And again, notice that the double not is just, that first one is just indicating that it goes with beta not. And the second one is indicating that it goes this is really the first coefficient. So this is like the intercept of the intercepts. And the gamma not is really going to be the overall expected value on whatever y is. And so a school's mean, the school predicted mean, or the school true mean, beta sub not j, is a function of the overall mean plus the deviation of the school from that overall mean. So you can imagine here that we've really sort of said, we've sort of broken things into 3 pieces. We say, okay, there's sort of this overall mean. On average, this is where people are. But then schools vary from each other. And so you can imagine a deviation of the school from the overall average. And that is really what's captured by that u sub not j. And then there's the deviation of the person from their school's average, or from their school mean. And that's really what the r sub ij is capturing. All right, so very simple model. We have no predictors, but the interesting thing here is that we can actually use this to look at partitioning the variance across, partitioning of variance across the within level and the between level, or across the within school level and the between school level. So we can combine this into one combined equation. And again, this is how we're going to actually write the code when we run these models in a multi-level framework. We'll always be writing the combined model. The combined model says, okay, y sub ij is a function of gamma not, right? Again, the overall mean, u sub not j, the deviation of school j from that overall mean, and r sub ij, the deviation of person I from their school J or their cluster J mean. And again, even with no predictors in our model, we still have this complex combination of residuals that give us the overall error term. And it's really the residual structure that separates multi-level or mixed models from normal linear regression models. So already here with no predictors, we have a multi-level or a mixed model, and we're doing something that we couldn't have done last semester in multiple regression. Okay, so again, this is really important. We can take those two residuals and we can compute the variances of those two residuals. And we assume that those residuals are independent of each other, right? And so those variances are going to not have a covariance between them. So, whether you're higher or lower than your school's mean, that has no relationship to whether your school is higher or lower than the overall mean. And we're actually making the assumption that there is no covariance between those two error terms. And because we make the assumption that there's no covariance between those two error terms, then we can actually add those two variances together to get the total variance in the outcome variable. So the total variance in Y is just the variance in U sub naught J plus the variance in R sub ij. But we have some very specific symbols that we're going to use in this class. Tau naught naught is the symbol that we're going to use to indicate the variance in the randomly varying intercepts. Okay, so, or the variance in I should really say the variance in U sub naught J, which is the error term that's associated with the intercepts. So that's tau naught naught. Again, that's the variance in the, at level 2. So it's this level 2 residual variance. And sigma squared is our level 1 variance, or our level 1 residual variance. So because we have no predictors in the model, there really aren't exactly residual variances yet in some sense, right? We can take the tau naught naught plus sigma squared, and that will give us the overall variance in our outcome variable, which is nice. And then that actually is going to, I'm going to skip over some of these slides. That's actually then going to become the denominator for our computation of the intra-class correlation coefficient. So the intra-class correlation coefficient, or the ICC, and the Greek letter that we use to denote the ICC, by the way, is a rho. I'll usually put ICC on things, but if you see rho, that's also indicative of the intra-class correlation coefficient often. So the ICC is the proportion of variance in the outcome variable that lies between those level 2 units. So it's the proportion of variance that's explained by the clustering, like the cluster or the grouping structure. And it's also, interestingly, the expected correlation between any two randomly chosen units within the same cluster. So how do we compute that intra-class correlation coefficient? Well, we just take tau naught naught. Again, that's the variance in U sub naught J, right? We take tau naught naught and we divide it by the total variance in Y. And the total variance in Y, we just said, is tau naught naught plus sigma squared. So to get our measure of the intra-class correlation coefficient, we just take tau naught naught divided by the total variance in Y, which is tau naught naught plus sigma squared. So this is a very easy computation. Again, let's talk about the random coefficients model now. So for the random coefficients model, we have now added a predictor, x sub ij. In our example in class, this is SES. And remember, we grand mean centered SES. So now we have y sub ij is predicted by the intercept. The intercept is always when everything in the model, when all the other predictors are 0. So again, we have an intercept for each of our J schools, right? Theoretically, there's an intercept for each of our J schools. And we also have a beta 1 slope, which is again unstandardized, But we have an unstandardized regression coefficient that captures the slope, the SES slope, which is really telling us about how well does SES predict math achievement. And that varies by school as well. We can see that sub J is telling us that we have a different regression, we potentially have a different regression slope in every cluster or in every school. And again, we have our R sub ij residual term. But now think about this. If my X variable actually helps to predict people's scores, so if SES is a good predictor, then what should happen to that R sub ij? What should happen to that residual? Well, it should get smaller, right? And I guess we can also think now that that would be true in multiple regression, but I guess the one little wrinkle that we want to think about is that, remember, we've actually got a much more complex error structure here. So I suppose, as we talked about yesterday, it would be possible for a level 1 predictor to help to explain some of the level 2 residual variance. But let's just think about this. Let's just think about level 1 for right now. If knowing a person's SES can help to predict how well they do in terms of their math achievement, right? Within, and again, thinking within clusters here, because really the R sub ij is now this within cluster variance. If knowing their SES can help to explain some of the within cluster variance in math achievement, that's really the best way to think about this, because again, we've got these different variance components at different levels. Then the variance in R sub ij is going to get smaller. And if the variance in R sub ij is getting smaller, that means, oh, hey, SES is helping us to explain some of the within cluster variance in math achievement. And again, if you think back to what R squared is, I mean, we can think about R squared as the proportion of variance explained in an outcome variable, but it also, R squared is also a function of 1 minus the unexplained variance over the total variance, right? Again, thinking back to multiple regression class. So as we decrease the within cluster residual variance, we're really saying, oh, hey, we're explaining variance in the outcome within cluster variance in the outcome variable using this predictor. Okay, so we're good on that equation. Now let's look at level 2. So now again, we take our randomly varying coefficients from level 1, our beta naught j and our beta 1j, and they now become our dependent variables, right? And now here we don't have any predictors at level 2, but we're saying the randomly varying, we're saying beta sub naught j is predicted by gamma naught naught, which is a fixed effect, right? It's just the overall intercept. It's like the overall predicted math achievement when SES is equal to 0 plus U sub naught j. And it's really this U sub naught j that's allowing those beta sub naught j's to vary across cluster. Because imagine if I take U sub naught j out, right? Let's see, can I reach this? You're going to be able to hear me very well, but I'm going to walk over here. Imagine I take the U sub naught j out of there, right? Now I'm saying beta sub naught j, right? The intercept for each of the j clusters is just gamma naught naught, right? So actually, in this case, we don't actually have different intercept values for different clusters because I took away the U sub naught j. So I took away the ability for gamma naught naught to actually vary across the clusters. It is that U sub naught j that actually is giving the ability to have different intercepts across the different clusters. So if I take that out, right, then I don't have randomly varying intercepts anymore. Now let's imagine this. What if I take out the U sub 1j? well, now I don't have randomly varying intercepts or randomly varying slopes, right? Because I'm just saying, well, beta sub naught j is equal to gamma naught naught, and beta sub 1j is equal to gamma 1 naught. And actually, if you do that, you would substitute in, hold on. Substitute in gamma naught naught times, well, what's the intercept? So times 1 plus gamma 1 naught times our x variable, SES, plus r sub ij. And I know that the notation looks really different, but if you stop and think about it, that's just a simple linear regression model. So again, it's really having these U terms that makes this a multi-level model. So let me come back over here for a sec. But I can, let me see. I could have a model like this, right? I could have a model that where I don't allow the coefficient for the SES slope to randomly vary across schools. If I get rid of that U sub 1j, that's what I call a random intercept model, because only the intercept is allowed to vary. A random coefficients model allows the intercept and at least one of the slopes, because we could have multiple slopes. Right now we only have one, but a random coefficients model allows the intercept and at least one of the slopes to randomly vary, and it does so by allowing for these error terms at the cluster level that say, hey, not all clusters, right? There's some overall slope, and then there's also this U sub 1j, which is really capturing the deviation of school J's slope from the overall slope. And again, I compute the variances for U sub naught j and U sub 1j, and those variances on 1, right? And those variance components are actually what become, those are the parameters in our model. We're actually going to estimate as the parameters in our model the fixed effects and the variance components. Now, I do want to allow these two variances to, I do want to allow these random effects to correlate with each other. So I do want to actually have what we would call an unstructured tau matrix, which means that I allow for those off-diagonal elements, those covariances, to be estimated. So what that looks like is, I should probably go to the prettier slide rather than scrawling it up here. So hold on a sec. There's my combined model. There we go. Here's my tau matrix. So what that looks like is I have a tau matrix where I'm saying, okay, I'm estimating the variance in U sub naught j, that's tau naught naught. I'm estimating the variance in U sub 1j, that's tau 1 1, and I'm estimating the covariance between these two, that's tau sub 1 naught or tau sub naught 1, whichever you want to call it. And this is what we would call an unstructured tau matrix, because we're estimating all of the off-diagonal elements. And in general, when we have multiple random effects, multiple U's at level 2, we're going to fit a tau matrix that is unstructured, that allows for the covariances among those random effects. And I'll talk more about why we do that a little later in the semester. So now I want to talk about these proportion reduction in variance at level 1 and the proportion reduction in variance at level 2. So I want to get some idea of the variance explained at level 1 or within schools by the variables in the model. And so what I can do is I can compute, again, this is like a pseudo R squared. This comes from Rodenbush and Breik. I just take, and by the way, you can see that I like the way my B's and F's are here as compared to what I had on the R markdown file. So we're going to take the sigma squared from the baseline model minus the sigma squared for the fitted model. So we're always going to take the sigma squared from the simpler model minus the sigma squared for the model that has, additional predictors in it, right? Divided by the sigma squared for that simpler model. And a good way to think about this is, we're always going to take the bigger sigma squared minus the smaller sigma squared. And of course, as we add predictors, the amount of residual variance should either stay the same or it should go down, right? Now we're using maximum likelihood estimation, so we'll see sometimes occasions, especially with the taus, where if we use certain types of centering techniques, that there might actually be a slight bump. But, we'll deal with that later. But basically, conceptually at least, we think, the simpler model should have the bigger sigma squared, and the more complex model should have the smaller sigma squared. And we want to get something here that's not going to be a negative number, right? Because you can never have a negative proportion of variance explained in a real R squared metric. And that's why we call this a pseudo R squared, really, because this is sort of a heuristic that we use. It isn't sort of the mathematical R squared that we got in multiple regression. We're going to talk when we get to Reitz and Sturba about some other ways of thinking about R squared or proportion of variance explained. Anyway, but for now, here's what we've got. This I find to be a very helpful way of thinking about how well I'm able to explain some of the level 1 variance in my model with a predictor or with a set of predictors. I do want to also express a caveat, though, that when I compute the proportion of variance explained measures, it's really best to do this with two models that have the same structure in terms of the variance components, right? So if I want the best way to look at the proportion of variance explained at level 1 by SES is to really look at this comparing sort of the null model and the random intercepts model. And the reason that I say that is because once I add in the random slopes, then you'll see that the random slopes actually, we get a variance component for the random slopes as well. And so now the random slopes have an opportunity to explain some of the overall variance. And where is that overall variance coming from? It could be, right? Some of it could be coming from sigma squared. And so in that way, that's maybe not a totally fair comparison. Now, people do actually use these proportion variance explains to compare, like an unconditional model to a random coefficients model. But I would say best practice really is, if I really want like a sort of the best, sort of most accurate or most fair comparison, I should compare two models that have the same random effects or variance covariance structure. Okay, so that's how I get variance explained at level 1. So here you go. And I have an example here actually where, it's our random coefficients model, that this is actually slightly different from the example that we did in class yesterday, because I have group mean centered SES on this slide, but the same idea holds true. The empty model, we had sigma squared of 39.15. In the new model, where we added SES group mean centered, the sigma squared was 36.83. I take 39.15 minus 36.83. I divide that by 39.15, and I get that proportion of level 1 variance that's actually accounted for by SES. And it turns out to be about 6%. So about 6% of the variance is accounted for by SES. Okay, so now let's talk about one model. Let's talk about one model that we didn't really get a chance to talk about yesterday. And I will go through this again next week as well. But now imagine we have a random coefficients model. Okay, so we are allowing SES to randomly vary across schools, and we're allowing the intercept to randomly vary across schools. And let's imagine now that we've grand mean centered SES, right? So now I could add a level 2 predictor, but what's interesting here is I can add sector, public private, as a level 2 predictor, both of the intercept and of the slopes. Now, I don't have to put the same predictor. I mean, I could have a predictor that I think only is going to predict differences in the randomly varying intercepts, or I could have a predictor that I think is only going to predict differences in the slopes or variability in the slopes, or I can have a predictor that does both. But let's think about what I'm really saying here. When I put in sector as a predictor of the intercept, I'm really saying that sector helps to predict schools' math achievement, again, after controlling for SES, because SES is grand mean centered. So I'm sort of equating all schools in terms of their SES, sort of holding SES constant at 0, which is the overall mean. I think, holding SES constant, some schools, right, have higher scores than other schools. And if I think that sector helps to explain why some schools have higher scores than other schools, that's where sector would be a predictor of that randomly varying intercept. Sector is a level 2 variable. It only varies between schools. It doesn't vary within schools, right? Every kid in the school is either in a public school or in a Catholic school. So there's no within school variability on the sector variable. So sector, we wouldn't expect to be able to explain any within school variance, right? But it might be able to explain between school variance. And again, here, because it's a predictor of the randomly varying intercepts, we're going to look and see, can sector help to explain any of the between school variance in those intercepts, right? In those randomly varying intercepts. And then in the second equation, I'm saying, okay, maybe sector helps to explain why slopes vary across schools. Some schools have steeper SES slopes, some schools have flatter SES slopes, right? SES is a better predictor of math achievement in some schools than others. If sector can help us to explain why SES is a better predictor of math achievement in some schools than others, then that's really what this gamma 11 is getting at. And remember, we said gamma 11 is a cross-level interaction because we're really talking about what's the effective sector on the effective SES on math achievement, right? Which I know sounds like a mouthful, but if you really think about it, it makes sense. What's the effective sector on those SES slopes, which is really saying what's the effective sector on the effective SES on math achievement. And again, if sector helps to explain some of the variation in those SES slopes, then that U sub 1j, that should decrease, right? And we can get an idea of how much variation, what proportion of variability in the intercepts and slopes are explained by the sector variable. And we're going to use the proportion of variance explained at level 2. Oops. Which I'm going to jump to that. Here we go. The proportion of reduction in variance at level 2, we can think about, again, the variance explained in the slope at level 2 by whatever set of, level 2 variables you have. You can use the tau from the baseline model, the simpler model, minus the tau for the more complex model, divided by the tau for the baseline model. So, and we do the same thing for the proportion of variances explained in the intercepts. So we can take the tau naught for the simpler model minus the tau naught for the fuller model divided by the tau naught for the baseline model, right? So we can figure out what proportion of variance in the randomly varying intercepts is explained by sector, what proportion of variance in the randomly varying slopes is explained by sector. And again, we would not expect sector to be able to explain any of the within school variance because sector only varies across schools, right? So how can something that is totally constant within schools, how could it possibly explain within school variance? All right, so a level 1 coefficient, right, then what we're really saying here is, let's think about our SES slope, our beta sub 1j. That level 1 coefficient can have both non-random and random sources of variation. The non-random source of variation would really be that gamma 1 times sector, or more generally W, right? Because notice that gamma 1, that's not, when I say it's not non-randomly varying, it's not randomly varying across clusters. We only have, right? We only have one estimate of gamma 1, and that's explaining, right? That cross-level interaction is actually helping to explain variability in the SES slopes, but it itself, right, is just one coefficient for the whole sample. Whereas the U sub 1j, again, notice that we have a U sub 1j for every cluster, for every school in our sample. So that's randomly varying, or a random source of variation. So when we build these models at level 2, when we put in these fixed effects, we can sort of think about those as non-random, right? We've got these variables that are sort of non-randomly varying coefficients that are helping to explain variability, right? And then the variability that isn't explained by those coefficients, that's still sitting in the U sub 1j, which is random variability across schools, even after accounting for whatever our level 2 models are. Oh, I guess I should have shown that a minute ago. So here are non-random sources. Again, notice no subscripts here on the gammas, right? We've only got one gamma 1 not, and 1 gamma 1. But then notice here, right, our U sub 1j, we're going to have a U sub 1 for every cluster. So this is what I mean by sort of random variance, or random variation. Okay, I'm going to skip that. Hold on. And I'm going to stop the slides, actually, and show. And let me just quickly turn attention to R. So I'm going to pause for a second and come back once I've got R set up, if I can pull that off. Okay, so here we are in R. Let me just say a couple of things before I get started. Before next class, please make sure you have an up-to-date version of R and RStudio, especially if you're planning to use your laptop in class. And also make sure you download RTools 4.2 and install RTools 4.2 on your computer. And then also make sure to have installed all of the packages that are on the R Markdown file that I gave you last week, so that all of the packages are installed. So make sure that your computer is ready to go. Right now, I've got R Markdown, and I did actually already call the libraries, and I've got all the packages installed that I need, and I opened up my R Markdown file, and this is also really important. Make sure you save in a folder. Don't try to run from Husky CT. Don't try to run from the courses folder. And don't just plop on the desktop. Put in a folder the data file and the R Markdown file. And if you create a separate file and it has the R Markdown file and the data file, R Markdown will find the data. If not, then you've got to give the path name for where that data is sitting, and that's like a little bit more of a pain in the butt, but it's totally doable. But I'm not going to show that right now. So here we go. First thing I'm going to do is read my data file into R, right? And that's that code, and there it is. Hooray. And then just remember that I need to do some cleanup before a little bit of recoding before I get started. The most important thing, and this is super important, is that you're going to have to tell R that your cluster variable, which here is school ID, but whatever it might be for your other data sets, you need to tell it that your cluster variable is a factor. And remember, a factor is kind of like a categorical variable, but it can have many, many, many levels, right? And so I think we tend to think of categorical variables as being like dichotomous or trichotomous or something like that. In this case, we have 160 levels of this categorical variable. Those 160 levels are 160 schools. That's fine. but we need to tell it that school ID is a factor variable. And then we also need to tell it that sector is a factor variable. That doesn't really matter actually for running the multi-level model, but it does matter for some of the graphing that we might do. So we run this and we make sure to say that our school ID is a factor variable. I'm going to skip through the graphs right now. You have all the code for the graphs. And then I'm just going to show you again what models, what the basic models are that we've talked about. So in our first model, again, we've got model 1. And this is just going to be our unconditional random effects ANOVA model. So we have no predictors. And remember, because we have no predictors, we're saying math achievement is a function of the intercept, and the intercept is designated by a 1. So math achievement is a function of the intercept. And then this piece in here, in the parentheses, that's telling about the random effects. So the fixed effects portion of the model is always going to be out here. And then we're going to sort of talk about the random effects portion of the model in the parentheses. So the random effects 1 bar school ID just means I'm allowing for a randomly varying intercept. So I'm saying math achievement is predicted by a fixed intercept, right? And a randomly varying intercept. The fixed intercept is going to be my gamma naught. And the randomly varying intercept is going to allow for that U sub naught J. And then I need to tell it what my data file is. And then the easiest way to get sort of the relatively complete output is to say summary model 1. And then it will display the summary information for model 1. So it's running. It always takes a tiny minute to run these multi-level models. If you have really complex ones, it can take quite a while. So here we go. So what we see here, it gives our random effects first, and really we're really interested in the variances, right, for those random effects, the variance components. So we can see the variance for school ID is 8.614, it says variance for school ID, but again, that's really the variance of the randomly varying intercepts. And the variance at level 1, the sigma squared, is 39.148. And then the only other parameter that we're really interested in here is what's the sort of model predicted math achievement. Again, we got nothing else in the model here. So basically this should be very close to sort of the overall mean, or basically be the overall mean. And that's 12.637. So I showed how you can actually use this data. You can use this little function here that I created. If you just run that function, now you'll have access to an ICC function to run the ICC for model 1. And remember, the ICC is just the tau naught divided by the sigma squared plus tau naught. So we get 0.18 there. Great. And now let's go to model 2. For model 2, and actually, with the Wrights and Sturba package, if you just run the Wrights and Sturba package, the R2MLM on the totally unconditional model, you'll see that you actually get the ICC there as well. So there you go. You see that same 0.18. Okay, which that trick's not necessarily going to work for a conditional model, but it does work with the unconditional model if you don't have that code handy and you don't feel like writing a little function or finding somebody else who wrote a little function, because lots of other people have. Okay, now I want to grand mean center my HSB variable. I'm using this mutate function that's actually from the tidyverse, from the dplyr package. So you're going to need to make sure that you have that library called before you actually run this. And all I'm saying is, okay, the HSB data file, right? I'm going to sort of take the old HSB data file. I'm going to mutate, and I'm going to create this new variable. That's the mutation, if you will. I'm going to create SES_C, centered SES, by taking SES from the HSB data set minus the mean of SES in the HSB data set. And when I run that, I get actually a grand mean centered variable. And then I can come to model 2. And in model 2, I have SES grand mean centered, but I only have a randomly varying intercept. So here I've dropped the 1. I could have 1 plus SESC. That wouldn't cause a problem to have the 1 plus, but I don't need to say anything about the intercept because as soon as I have a predictor in the model, it assumes, unless I say otherwise, that I want an intercept and a slope. So I can just say math achievement tilde SESC, which looks just like what you would say like in LM for a regular regression model. But now I've got this, right? I've got to tell it about sort of the structure of my random effects, right? I need to tell it about what use do I want. And here I'm saying the same thing I said in my last model, model 1, I want a randomly varying intercept. So that's 1 bar school ID. I didn't say anything about wanting a randomly varying slope here, so I'm not going to get one. So if I run this, oops, sorry, ran the wrong thing there. Let me take summary off here. If I run this, then I'm actually going to get, wait for it. Okay, there it is. Then I'm going to get this output. So now the 12.6, let's call it 12.66, that intercept is actually predicted math achievement or expected math achievement when SES is at the overall mean, because I grand mean centered SES. It's when SES is 0, but SES is 0 at the overall mean. So basically, right, on average, when, you know, when somebody's got average, you know, when we're talking about average, a person of average SES, right, or we would expect, you know, not knowing anything else, we'd expect to see a math achievement at 12.66, right? And that, again, should be pretty close to the overall average. And the SESC, that's the slope. That's the SES slope. So this is saying, okay, for every point increase in SES, we expect to see a corresponding 2.39 point increase in math achievement. And remember, we haven't allowed that SES slope to vary across schools, so we're really kind of forcing all of those regression slopes for each of the 160 schools to be parallel. So we're allowing for different intercepts across the 160 schools, but not different slopes. And that's really what we see here. And then we can, oops, I should go back up here to our variance components. We can see that the variance went down a little bit within schools, right? And I think we computed this, it was a little less than 5% decrease in the within school variance. So we're explaining about 5% of the within school variance with the SES variable. But we see that we're explaining like close to 50% of the between school variance with SES. And we talked about the fact that that's because actually there's a ton of between school variance in SES, right? Okay, so then let's go to model 3. Hold on. Scrolling down. Oops, actually, model 4. Model 4 is good. Model 4 is what I want to talk about. So let's go to model 4. And in model 4, actually, this is the model, the last model we talked about yesterday. This is the random coefficients model. So notice what's different here. The fixed effects part of the model looks just like it did in model 2, right? Math achievement tilde SESC, right? So SES is a predictor of math achievement. But what's different here is that now I'm saying, okay, yeah, but I want a randomly varying intercept and I want to allow the SES slope to randomly vary. And I think I mentioned yesterday that just like you can drop the intercept, the one up here in the fixed effects part, you can also drop the intercept here and just say SESC underscore school, or not underscore, bar school ID, and it will again assume that you actually want a randomly varying intercept. So that's why I say, I actually have that written out here, and I say alternatively you can drop the 1. And so you'll see that these two sets of codes will give you identical results. So let's go ahead and run that. And then finally, after we run this and after we see our results. Okay, here we go. Perfect. So now we see, again, actually our estimates here, our gammas, they don't look so different, which kind of makes sense. I mean, I've added a randomly varying slope, but you know, I have that hasn't actually changed my fixed effects estimates very much. I mean, I guess conceivably it could, but it doesn't here. But what I do see here is that I got a much more complicated variance covariance structure. And so what I have here are, I have the variance for the between school variance in the intercepts, the between school variance in the slopes, right? That's what that 0.4129 is. It's the between school variance in the slopes. I've got the within school variance, the 36.83. So this is really new, this 0.413. We didn't have anything like that before because we weren't allowing the slopes to randomly vary. And then I actually get over here, and this is in a, it only displays in a standardized metric, the correlation. I get the correlation between the randomly varying slopes and intercepts. And we'll have a lot more to say about that correlation later, but just notice for now that I am actually estimating 4 different variance components. I'm estimating the sigma squared, which is that within school variance component, and then I'm estimating the tau naught and the tau 11, and then I'm also estimating the covariance between tau naught and tau 11, which is tau naught 1, which the standardized version of that is this negative 0.11. All right. And I think I will just quickly, really quickly, show you model 4. Let's see. No, I won't. I will stop there actually, because that's where we stopped yesterday. So I'll stop this here, and then we'll pick up next week with a brief review of all of this, and then we'll actually build our model where we add sector as a predictor of both the intercepts and the slopes. All right, thanks. I hope this was helpful.